This video covers Stat 454, Chapter 4, Section 5, the simplex method. This section relies heavily on elementary row operations. If you need to be refreshed on elementary row operations and matrix forms, watch the video linked in the description below to refresh yourself, and then come back and follow along with the rest of the simplex method. The simplex algorithm is a 9-step algorithm. I'll go through all of them descriptively first, and then I'll show you a step-by-step process of it being used to solve an LP. Step 1, put the LP into standard form. That's when you take an LP and replace all of the inequality constraints with equality constraints, either through slack or excess variables, as appropriate. Step 2, put the LP into a simplex tableau. All a simplex tableau is a nice, consistently written representation of the LP so that you can keep all of the variables in order. Step 3, select the non-basic variables. Remember that non-basic variables are variables we choose to equal 0. And then once we make that decision, observe that each row will decide a value of a particular basic variable. By putting it in the right form and choosing the right non-basic variables, we will be able to read the basic variables directly off of the table. Once we're at that stage, we're finally at a step to begin increasing the value of Z. Choose the entering variable, just like we did in the last video I posted. We choose the steepest increase, and it will turn out after we do all of our rewriting that the steepest increase will correspond to the most negative coefficient in the objective function value. Then we're going to decide which variable we're going to actually get a value from. That's going to be from the pivot row process, where we select the smallest non-negative ratio, just like we did in the last example. And then this is where the elementary row operations come in. We're going to eliminate all of the other values above and below so that we fix in the value of the entering variable. We'll use the new table to update the basic and non-basic variables and repeat that process until all of the coefficients in the objective function row are non-positive. When we no longer have values that increase Z, that means Z is at its highest value, and we can stop the simplex method. I'm going to look at it in practice on this LP. The simplex method solves maximization problems. So we're going to try to maximize Z equals 60x1 plus 30x2 plus 20x3, subject to these constraints. 8x1 plus 6x2 plus x3 less than or equal to 48. 4x1 plus 2x2 plus 1.5x3 less than or equal to 20. 2x1 plus 1.5x2 plus 0.5x3 less than or equal to 8. And then finally x2 less than or equal to 5, where all of these values are greater than or equal to 0. Remember that the first step is to put the LP into the standard form. We have to turn all of these less than or equal to constraints into equality constraints through the use of slack variables. And the first equation gets a slack variable of S1, the second of S2, so on and so forth. Do not forget to include sign restrictions even on the slack variable. All of the variables have to be non-negative. Now that we've done that, this is the representation of the simplex table that we are going to look at. Notice I've done a few things to make this table happen. I've called row 0 the row that applies to the objective function. And on the objective function, instead of thinking of it as z equals some quantities, I've subtracted the right-hand variables over to the left-hand side, giving me z minus, minus, and minus. Once I do all of those subtractions, the only thing remaining on the right-hand side is this value of z equal to 0. And then I just go constraint 1, row 1, constraint 2, row 2, etc., making sure I position all of the variables in the corresponding row. So x1 variables are all in a row, column. x1 variables are all in a column. x2 variables are all in a column. x3, s1, s2, s3, and s4. Okay, now we have to make some decisions for basic variables and non-basic variables. The trick to choosing your basic variables is choose the basic variables in such a way that they make the remaining non-basic variables very easy to read off of the table. So for example, if all of these coefficients, this row of 3, row of 3, row of 3, if all of these variables were equal to 0, then the remaining variables on the right-hand side would be very easy to read their values. If I set x1, x2, and x3 equal to 0, that means s1 equals 48, s2 equals 20, s3 equals 8, and s4 equals 5. Those non-basic variables come right out of the table. So I make these choices, and that forces these values of the basic variables. Now, let's decide what the entering variable is. I choose an entering variable that most quickly increases z with a choice of 60, 30, and 20. I obviously choose x1. So x1 is the entering variable. Now I need to decide how much I can increase x1 by. Taking ratios. Divide 48 by 8. Divide 20 by 4. And divide 8 by 2. I see there's a typo right here. This should say 48 over 8 equals 6. 20 over 4 equals 5, and 8 over 2 equals 4. Just like in the last video, I will choose the smallest of these ratios. That ratio is row 3. Now that I've decided that row 3 is the place where I am going to increase x1, I want to eliminate all of the appearances of x1 above and below row 3 using elementary row operations. So I want to use elementary row operations to eliminate x1 in row 0, row 1, and row 2. Does not apply in row 4. These are the elementary row operations that will get the job done. They all work by scaling the coefficient of 2 to match 68 and 4. That's going to be 30, 4, and 2 respectively. I choose the opposite sign in order to make the quantities cancel each other out. And by doing these 3 elementary row operations, I end up with this new table. Let's take a look at the form of this table and see what pieces of information we can get. The very first one, notice z. Since there's nothing above or below it, I think it will be a basic variable. Z equals 240 is a new objective function value. I think we all agree that 240 is greater than 0. In this next row, there's nothing above or below x1, so x1 equals 4 is a new basic variable value. This coefficient of x2 has become positive. Remember that we shifted the coefficients over to the opposite side, so this actually corresponds to a negative coefficient in the objective row. That means x2, if I increase it, is going to decrease the function values. Similar concept in this row, -5. If I move it over to the other side, that's a +5. Increasing x3 will increase z. Same type of reading in these two columns. S1 equals 16 is a basic variable value. S2 equals 4 is a basic variable value. 30 S3 will decrease z. And then S4 equals 5 is a basic variable value. Now that I have this new tableau, I am going to repeat the process here. Choose the most negative. That's -5. So x3 is the entering variable. I will now take x3 in each of these rows and perform a ratio test. 16 over 1, 4 over 0.5, and 4 over 0.25. And on this last one, not applicable because it doesn't appear. Excuse me, 16 over -1. This negative value is not allowed. We have a +8, and then a +16, and then an undefined ratio. Remember that I want to choose the smallest amongst the list of 8 and 16. That's 8. So row 2 is the new pivot row. I am going to eliminate values for above and below x3 using row 2. I'm going to eliminate this 5, this 1, and this quarter. Using the same principles, scale the row to 1 so everything cancels nicely, and then these 1, 2, 3 elementary row operations, canceling out these 1, 2, 3 coefficients. Once I perform that process on this table, you'll notice that x3 has nothing above it, just like x1 had nothing above it previously. Now, let's take a look at what this table tells us using the same principles. Remember that the coefficients were moved over to the opposite side, so this would correspond to -5x2. That means I don't want to increase x2. This would correspond to -10s2. This means I don't want to increase s2, and this corresponds to -10s3, so I don't want to increase x3. I am at a point where I can no longer increase z. That means z equal to 280 is the optimal function value. And reading off these isolated columns will tell me the objective, the variables, reading off of these columns will tell me the variable values that maximize z. X1 is by itself, so x1 equals 2 is a basic variable. X3 is by itself, so x3 equals 8 is a basic variable. S1 equals 24, so we have a slack of 24, and S4 equals 5, we have another slack of 5. The very last thing I want to mention is writing down all of these variable names can become tedious, so you can put this in a strictly matrix form. Here's a matrix form representation of this LP and this optimal table. Notice all of the coefficients in row 0 are positive, indicating a maximum value. This completes all of the content associated to Chapter 4, Section 5, the simplex method.